Our next unit dives into real numbers and properties about them. So we're going to start out by talking about prime and composite numbers. So we're going to go over all the different classifications within a real number. So we know there are tons and tons and tons of numbers, 1, 2, 3, 4, 5, 6. You have everything in between them too, 1.7. You have fractions like 5/2. You have numbers that don't have a nice pattern like pi, that's 3.14159, and it keeps going on forever. So we're going to start with the classification of natural numbers. Every single classification has a special symbol for it. So the way we do the natural numbers is we do kind of like a bold-faced N. Just doesn't have like it filled in. Natural numbers are essentially kind of like counting numbers. Now this is going to be book specific, but our book does not include 0 in natural numbers. So natural numbers start at 1, then go to 2, 3, 4, and then it keeps going. It's all of the nice numbers, okay? So in this section, we're going to work with these, and we're going to talk about divisibility, prime numbers, things like that. So first, we're going to talk about what divisibility is. We say A is divisible by B if the operation leaves a remainder of 0. So we're going to work with a common number, 24, because this breaks down really nicely. There's lots of things it's divisible by, but it's definitely divisible by 6. Because if you plug in your calculator, 24 divided by 6 gives you 4. There's absolutely nothing left over. You get a nice natural number as the result. However, 24 is not divisible by the number 5, because if you take 24 and divide it by 5 in your calculator, you're going to see this ends up with 4.8. So it goes in 4 times, but there is some kind of remainder left over. Because if you think 4 times 5 gives you 20, and that would leave you with a remainder of 4, okay? So to say that something is divisible or divides nicely into the other, we would write 6 with a bar and then 24. So we write this to say that 6 divides into 24. The number 6 is also called the divisor. Okay? So what we're going to be doing predominantly in this section is determining if two numbers, if one divides another. But more so, we're going to talk about breaking a number down into different factors. So we're going to see, okay, 24, how can I break that down into the smallest component that makes it up? So anytime we figure this out, when we break a number down based on what it's divisible by, we're breaking it into something called factors. Okay? To give you some examples, 24 is a great one because it's divisible by a lot of things. We know we can write this as 4 times 6. So we'd say 4 and 6 are factors of 24. But you can really do this other ways. Well, 24 is also 8 times 3. So you can say 8 and 3 are factors of 24. You can also do 12 times 2. And then you can also do 24 times 1. All of these are ways to break down 24. If you can't do this with a number, you're really only left with one possibility, the number times 1. In that case, that is a prime number. So a prime number is a natural number greater than 1 that only has itself and its 1 as factors, meaning it is not divisible by anything other than 1 and itself. So the number 2 is a prime number, can only be divided by 2 or 1. 3 is a prime number, divisible by 3 and 1 only. 5 is another example. Then 7, 11, 13, 17, and really this list keeps on going. These are all prime numbers. They cannot be divided nicely by anything other than the number and 1. Okay. If you can break a number down into something else, so it's divisible by other things, that's going to be called a composite number. So a composite number is a natural number that's divisible by something other than 1 or itself. And so 24 is a prime example of that. We can write it as 6 times 4, 8 times 3, 2 times 12, or any variation or rearrangement. But you can break it down, so this is a composite number. So every natural number is going to be one of these two things. It's either prime or it's composite. The only distinction is the number 1. That one was neither prime nor composite. It's just kind of standalone. But the main thing we can actually do, if we have a composite number, we are always going to be able to break it down into its primes. Every composite number can be written as the product of prime numbers. Okay? So to give you some examples of this, the number 9. You can write that as 3 times 3. And both of these are prime numbers. 15, you can write as 5 times 3. Also prime numbers. Well, 45, that one's a little bit harder. You could write this as 5 times 9. But this 9, I can actually break down further. So that's 5 times, and 9 can be written as 3 times 3. And then to clean this up a little bit, 3 times 3 is 3 squared. So that's 3 squared times 5. So in the end, I end up with just a product of prime numbers. So overall, this process is called prime factorization. Every single number that's composite, we can do this with, okay? This is actually something called the fundamental theorem of arithmetic. Every composite number can be expressed as the product of prime numbers in one way. Does not matter how you get there, it will only be expressed in one way. And to just kind of show you, we can do that with this 45 example. Instead, maybe you notice 45 is divisible by 3, so you write that as 3 times 15. And then the 15 you break down further, 15 is 3 times 5. So in the end, you still end up with the same prime factorization, even though I got there a different way. So every composite number is unique and has one prime factorization. The way we're actually going to figure this out is typically with a process using trees. So you want to figure out, can you break this down? What prime numbers is it divisible by? So we're going to try a few examples, and then we'll get more practice with this because we're going to talk about greatest common divisor and least common multiple of two numbers. So we're going to start with finding the prime factorization of the number. And we're going to start with the number 400. So the way I like to go about these is I write the number at the top. And I basically want to start dividing this by prime numbers. Maybe in your head you noticed immediately, oh, well, 400, that's 4 times 100. Great. So we could break it down based on that. But 4 and 100 are not prime numbers. However, I can keep breaking those down further. So 400 is 4 times 100. Well, 4 I can really write as 2 times 2. And both of these are prime, so they're going to be part of my prime factorization. Now going through 100, maybe you notice, oh yeah, okay, well 100 is 4 times 25. Well, neither of those are prime either. So instead, I'm going to break this 4 down more as 2 times 2. And now the end of my tree has led me to 2 prime numbers. And same thing, 25, I can write as 2 primes. That's 5 times 5. So if I look at the ends of all my branches, that's going to give me my prime factorization. So the number 400 we can write as if I go ahead and connect these, I have 4 2's. We have 2 times 2 times 2 times 2. And then I've got 2 5's. So that's times 5 times 5. Okay. So these are all the 2's from my branches, and these are all the 5's from my branches. So the way to concisely write this, 4 2's being multiplied is 2 to the 4th. And then 5 times 5 is really 5 to the 2nd. So this is my prime factorization, okay? Again, I could really do this a different way just to kind of show you. The better way would be to divide it by primes. It's going to create a bit of a longer tree, but it's still going to work out. So I'm going to take 400 and I'm going to start dividing it by these prime numbers and see what goes into it. So starting with 2, you can divide 400 by 2 and it leaves you with 200. Now I want to break down the 200 because this cannot be broken down anymore. That ends one branch. 200 we can then break down. That's divisible by 2. So that gives you 2 times 100. Well, 100 is even, so you can break that down as 2 times 50. And so again, I'm going to keep circling all of those prime values. Then 50 is also even. That's 2 times 25. So I've got my 4 2's in the same way. And then 25 is not divisible by 2, but it is divisible by 5, so we get 5 times 5. And so this one I think is a little bit cleaner to read because now I can easily see, well, I've got 4 2's and I've got 2 5's. So that gives me my prime factorization. For these next couple ones, I'm going to need a calculator, so I'm just going to pull this up on the side of the screen to help us out. So I need to figure out what prime numbers go into 513. So if I start with my smallest prime number, unfortunately 2 does not divide it nicely. So instead I'm going to go to my next prime number, which is 3. And in that case, I'm left with 171. So this breaks down as 3 times 171. And this is good because that is part of my prime factorization. Now again, that's not even, so it's not going to divide by 2. So I'm going to see, okay, is it divisible by my next prime number, which is 3? And in that case, it is. So I can break 171 down as 3 times 57. And now we keep going. We want to see, okay, is 57 divisible by anything? Definitely not 2. So let's try our next prime number. We need 57 divided by 3. And that does work out nicely. So that can be written as 3 times 19. And then 19, well, you could try to divide this by a bunch of things, but 19 actually is a prime number as well. So it will not be divisible by the numbers 2 through 18 at all. So really our prime factorization for 513 is we can write this as those ends of the branches, which is 3, 3, 3, and 19. So really that prime factorization is I have 3 3's and I have a single 19. Okay. So our last 2 examples are still going to involve finding this prime factorization, but we're going to utilize it to find the greatest common divisor and the least common multiple. So starting with the greatest common divisor, the greatest common divisor which you're often going to see me abbreviate as GCD, of two numbers is the largest number that divides into both of the numbers. So the biggest thing they are both divisible by, okay? So what I have to do to actually go through and find the greatest common divisor is figure out what is the prime factorization. And I'm going to utilize that to see what is the most number of primes that go into it. So we're going to walk through an example of this. We're going to find the greatest common divisor of 216 and 234. So my first step is to find the prime factorization of each of them. So I'm going to start with 216. So that's an even number. It's definitely divisible by 2. So I can write this as 2 times 108. And so that's one end of a branch. Well, that's definitely even again, so it's divisible by 2. So that's 2 times 54. And then 54, well, that's even, so divided by 2 again. That gives me 2 and 27. Now, unfortunately, 27 is not an even number, so it does not divide by 2. However, it does divide by 3. So this can be written as 3 times 9. And 3 is a prime number. And then 9, hopefully you don't need a calculator for this one, but that does break down as 3 times 3. So this is my prime factorization for 216. At this stage, I'm not going to write all of them out. 2 and 3 are the only prime numbers that make up this number. I have 3 2s and I have 3 3s. Okay. Now I want to do exactly the same thing with 234. So starting out, that's an even number, so let's divide it by 2. That gives me 2 and 117. So unfortunately, 117 is not an even number. Just to show you, if you divide that by 2, doesn't work out. So we're going to try the next prime number, which is 3. And that thankfully does work out nicely. So 117 can be written as 3 times 39. And then same thing, not even, so not divisible by 2, but it is divisible by 3. We get 3 and 13. And 13 is a prime number, so I cannot go further than that. So my prime factorization for 234 involves 2s, 3s, and 13s. I have a single 2, so I don't need to write an exponent on that. I have 2 3s, and again, I have a single 13, so you could put a 1 here if you want, but you don't need it, okay? Now what I want to do is to figure out my greatest common divisor. I'm going to compare the 2s. My greatest common divisor is the smallest number of 2s that will go in. Because if I look here, 234 is divisible by 2 only once. Even though this one is divisible by 2 3 times, the thing that's common is the smallest one. 2 will only go in a single time here. So there's no way I can divide 234 by 4 because I don't have 2 2s on this side. Just to show you, if you take 234 and divide it by 4, you do not get a nice value. So I only get one single 2 in my greatest common divisor. And then I want to pick the same, comparing the 3s, I pick the smallest number of them. So really only 2 3s will be my greatest common divisor. And then I look at my last prime number, which is 13. I have 1 over here, but I don't have any over here. I really have none. So in this case, 13 is not in my greatest common divisor because 216 is not divisible by 13. You get a really nasty number, okay? So for each prime factor, we're going to select the one with the smallest exponent common to each. So what I'm going to do is I'm going to go ahead and just copy and paste these here, just for convenience. And then what I want to do is I want to pick the smallest number of 2's, the smallest number of 3's, and the smallest number of 13's. Okay. And if you need to add in here that you have no 13's, you do exactly that. It's 13 to the 0. You have 1 2 here, and then you have 1 13 here. So my smallest number of 2's comes from this one. I have a single 2. My smallest number of 3's, if I compare them, is 2. So this is my smallest number of 3's, which is 3 squared. Okay. And then my smallest number of 13's is none of them, because one of them does not have anything. Okay. So what I'm going to do is I'm just going to go ahead and I'm going to then take the product of these three, and that is my greatest common divisor. So my GCD is going to be 2 times 3 squared, and then you have no 13, so that's 13 to the 0, which is 1. Really, 13 is not included in my greatest common divisor at all. So this leaves me with 2 times 9. So my GCD is going to be 18. And just to show you, if you take 216 and divide it by 18, you do get an answer. And 234 divided by 18 also gives you an answer. Okay. So that is my greatest common divisor. So the other thing that we can find is the least common multiple. So the names are kind of confusing because for the greatest common divisor, you pick the least number of factors. When I want to do the least common multiple, I'm going to do the opposite. I'm going to pick the most factors. So the least common multiple which you'll often abbreviate as LCM, of two natural numbers is the smallest number that they both divide into. So for an example, if we're trying to find the least common multiple of 144 and 300, I'm trying to find the smallest number that is divisible by 144 and also divisible by 300. So we still follow the same process. We start by finding the prime factorization of each. So starting with 144, and then we'll do 300. Again, it's really natural for you to say, okay, 144, 12 times 12, you can absolutely go that route to figure out what the prime factorization is. But then you get branches that are a little bit just messy looking. So instead, I'm going to start out by dividing this by 2 because it does divide nicely. So 144 you can write as 2 times 72. And that is one of my prime numbers. Then again, I want to break this down. It divides by 2 again. So we get 2 times 36. And 2 is a prime number. Then I want to see, is 36 divisible by 2? And indeed it is. That gives me 2 times 18. So another prime number at the end. Keep going. It's divisible by 2 again. And that leaves me with 9. And then at this point, 9 can be broken down as 3 times 3. So those are both prime numbers. So my number 144 is a product of 2's and 3's. I have 4 2's and 2 3's. Okay. Again, you absolutely can do this by doing 12 and 12, but it's just messier to read. Just to kind of show you, I'll do that over here and then just erase it. You could write this as 12 times 12, and then 12 you can break down in a couple different ways. You could say, okay, well that's 2 times 6, and this is 2 times 6. And 2 is a prime number. And then from here, 6 can be written as 2 times 3. So both of these branches are 2s and 3s. It just makes it a little bit muddled because the ends of your branches are mixed in. So these are all part of the prime factorization, and so are these. So you still end up with 1, 2, 3, 4 2s, and then 2 3s. It's just harder to read. Where here, you just kind of get to read clear down, and you get that final answer. So I like the longer trees a little bit more. Then if we look at 300, same thing. We'll start by dividing it by 2, and great, it does divide by 2. So we get 2 and 150. Then divides by 2 again, so that gives me 2 and 75. And then at this point, that does not divide nicely by 2, so that's the end of that. So we'll try dividing by 3, and fantastic, it does divide by 3. And then 25, unfortunately, has to be written as 5 times 5, so we get some new prime numbers in here. So 300 can be written as 2s, 3s, and 5s. We've got 2 2s, we've got a single 3, and then we've got 2 5s. Okay. So if I'm looking for a number that's divisible by 144 and also by 300, it's going to have 2s in its prime factorization. And I need both of these to divide in, so I actually want the larger quantity from them. I need it to be divisible by this number, so I need it to be divisible by the most amount of 2s that I have. So here we're doing the exact opposite. We're going to select each prime factor with the largest exponent from each factorization. So just going ahead and putting these here. I need the largest number of 2s, the largest number of 3s, and the largest number of 5s. I don't know why I wrote a 2 there. There we go. So going through and selecting that, this one has 4, this one has 2. So the most number of 2s I have is 2 to the 4th. Moving on to 3s, I've got 2 and I've got 1. So the most number is 2 of them. And then the most number of 5s, well, this is the only one that has 5s, so it's the biggest amount, 5 squared. So my least common multiple of these two numbers is then just the product of these. So 2 to the 4th, 3 squared, and 5 squared. Well, 2 to the 4th, you don't have a 4th button in your calculator, so you could type out 2 times 2 times 2. But on the phone calculator, you would do 2, then you would go ahead and press this exponent button, and then you press the exponent of 4. So 2 to the 4th is 16. 3 to the 2nd is 9, and then 5 to the 2nd is going to be 25. So if I take 16 times 9 times 29, the smallest number that is divisible by both 144 and 300 is going to be 3,600. So just to show you, if you divide it by 144, go. You do get a nice answer. And then 3,600 divided by 300 also gives you a nice answer. So this is the smallest number divisible by 144 and 300.